Imagine plugging your electric car in when you wake up, and before your coffee is even finished, the battery is full. Not 30 minutes, not an hour, 5 minutes. Then you get back in and drive hundreds of miles without thinking about charging again. It sounds impossible, but that is exactly why Toyota's latest solid-state battery claims have attracted so much attention. The numbers being discussed are almost absurd. Around 1,200 miles of claimed range, a full charge in minutes, and potentially a battery that is lighter, safer, and far more energy-dense than today's lithium-ion packs. But here's the interesting part. The real story isn't the number on the range display. It's what happens if Toyota can actually manufacture this technology at scale. Because if that happens, the biggest limitation of the electric vehicle may finally be disappearing. And Toyota already has a vehicle at the center of these claims, the alleged Toyota X1. The idea is simple but extraordinary. Build a vehicle around solid-state battery technology from the ground up, give it dramatically more range, and make charging so fast that an EV stop starts feeling more like filling a gasoline car. The claims surrounding the X1 include up to 1,200 miles of range, around 5-minute charging, and a potential price below $30,000. If those numbers become reality, this wouldn't simply be another new electric car. It could force the entire industry to rethink what an EV is supposed to be. But before we decide whether Toyota has actually changed the game, we need to understand the problem it is trying to solve. For roughly 3 decades, lithium-ion batteries have powered the electric revolution. They transformed phones, laptops, cameras, and eventually cars. But the same chemistry that made EVs possible also created some serious compromises. More range generally means more battery. More battery means more weight. And more weight means the car needs more energy just to move itself. Then there's charging. Even modern high-speed chargers can leave drivers waiting significantly longer than they would at a gasoline pump. And inside conventional lithium-ion batteries is a liquid electrolyte that can become dangerous when cells are severely damaged or overheated. That's where thermal runaway can occur, with heat spreading from one damaged cell to others. And then there is the supply chain. Lithium, nickel, cobalt, and the enormous global network required to extract, process, and transport these materials. In other words, the EV industry has spent decades building an incredible machine around a battery technology that still has limits. That's why solid-state batteries matter. The concept sounds almost deceptively simple. Move the liquid electrolyte and replace it with a solid material. In theory, that could improve safety while allowing engineers to store substantially more energy in the same space. But there was a reason this technology stayed in laboratories for so long. Solid materials expand and contract during charging, discharging, and temperature changes. Over thousands of cycles, microscopic cracks can form where those materials meet. Once those interfaces begin failing, performance suffers. This interface problem has been one of the biggest obstacles between an impressive prototype and a battery that can survive years inside millions of cars. And this is where Toyota claims it has found a way forward. While the EV spotlight was focused on Tesla and other electric car companies, Toyota was spending years developing battery technology behind the scenes. Its goal wasn't simply to make lithium-ion slightly better. It was to eventually replace it. The company's approach involves solid electrolyte materials designed to better tolerate repeated expansion and contraction. Then comes another critical piece: the anode. Conventional batteries can develop microscopic structures known as dendrites under certain conditions. Think of them as tiny branches growing where they shouldn't. They can reduce performance and contribute to internal short circuits. Toyota's proposed material approach is designed to suppress this problem. If those claims hold up outside controlled testing, the payoff could be enormous. Dramatically higher energy density without simply adding a larger battery. And this is where the numbers start getting interesting. If advanced lithium-ion cells are around 250 watt-hours per kilogram, pushing energy density significantly higher means you can potentially store far more energy without carrying the same amount of battery weight. Less weight can mean lower energy consumption, which can create even more range. And a smaller, lighter battery can change the way the entire vehicle is designed. But Toyota's most dramatic claim isn't actually the range, it's charging. Today's fastest public chargers can reach hundreds of kilowatts. Toyota's proposed system is claimed to reach around 2.2 megawatts. If the battery can safely accept that level of power, charging could become almost unrecognizable compared with today's EV experience. Pull in, plug in, take a short break, come back, leave. But there's an obvious problem: the power grid. A charging station capable of delivering megawatts of power can't simply demand enormous bursts of electricity from the grid every time several vehicles arrive. Toyota's proposed solution is to put large stationary batteries at the charging station. The grid can slowly charge that storage system, and when a vehicle arrives, the station's battery delivers the massive burst. That means ultra-fast charging becomes not just a battery problem, but an infrastructure solution as well. There is another potential advantage: safety. A solid electrolyte doesn't contain the same flammable liquid found in conventional lithium-ion batteries. That doesn't make a solid-state battery impossible to damage, but it could fundamentally change how the battery behaves during severe failures. And Toyota's concept goes even further with cell-to-frame integration. Instead of treating the battery as a heavy box attached underneath the car, the battery can become part of the vehicle's structural architecture. That could reduce unnecessary material, improve rigidity, and lower weight. Suddenly, the battery isn't just storing energy, it's becoming part of the vehicle itself. But there's one question that matters more than every laboratory number we've discussed. Can Toyota actually build this technology cheaply and in large enough quantities? Because making one impressive battery is easy compared with making millions. Production has to be repeatable. Materials have to be available. Defect rates have to fall. Costs have to come down. Toyota's manufacturing experience could give it an advantage here. The company already knows how to turn complicated engineering into mass-produced vehicles. And if its solid-state production systems can scale, that manufacturing experience could ultimately matter just as much as the battery chemistry itself. And this is exactly where I want you to remember modern discovery. If you enjoy following breakthroughs in EVs, batteries, futuristic cars, and the technology that could change transportation, subscribe now. Because the most interesting part of this story isn't what Toyota claims today. It's what happens when these batteries start appearing in real vehicles and real factories. Because we also need to slow down before accepting every number as reality. A claimed 1,200-mile range does not automatically mean an average driver will see 1,200 miles. Testing conditions matter. Highway speeds matter. Temperature matters. Heating and air conditioning matter. Driving style matters. The same goes for 5-minute charging. Achieving that number consistently across different temperatures and battery conditions is a completely different challenge. And then there's the alleged sub-$30,000 price. If Toyota can actually achieve that, it would be revolutionary. But until large-scale production proves the economics, it's a target, not something consumers can assume is guaranteed. Most importantly, long-term durability still needs to be demonstrated in ordinary vehicles driven by ordinary people for years. And Toyota isn't racing alone. CATL is developing its own solid-state technology. Samsung SDI is working on solid-state batteries in South Korea. In the United States, companies including QuantumScape and Solid Power are also trying to solve the same problem. Everyone understands what's at stake. Whoever masters solid-state batteries first won't simply build a better battery. They could gain a major advantage in the next generation of the automotive industry. Toyota's potential advantage is scale: factories, suppliers, engineers, global distribution, and decades of experience manufacturing vehicles. That's the difference between an impressive laboratory prototype and a technology that could eventually sit in millions of driveways. And the consequences could extend far beyond cars. If an affordable EV could eventually travel close to 1,000 real-world miles and recharge in roughly the time it takes to make a short stop, range anxiety could become far less important. Long-distance electric travel could become dramatically easier. But high-density batteries could also be used for home energy storage, allowing solar power generated during the day to be stored and used later. At a much larger scale, batteries could store excess renewable energy and release it when demand rises. And if energy density continues improving, applications could eventually extend into drones and electric aviation. The potential impact isn't limited to the driveway. It reaches into the energy system itself. For 30 years, lithium-ion batteries gave the EV revolution its foundation. But they also created limitations: weight, charging time, heat, safety concerns, and complicated material supply chains. Solid-state technology could potentially attack several of those problems at once, but there is one distinction we cannot ignore. Potential is not proof. Toyota still has to manufacture these batteries at enormous scale. It has to hit the promised cost. It has to demonstrate real-world range. And most importantly, those batteries have to survive years of real-world use. That is the test that matters, because the battery race has changed. The question is no longer simply, can solid-state batteries work? The question is, who can make them work at scale? And if Toyota really can, the biggest change may not be a car that charges in 5 minutes. It may be the moment the battery itself stops being the biggest limitation of the electric vehicle. That could change how we drive, how we charge, how we store electricity, and potentially how we power entire cities. So, is Toyota actually bringing the future into the present? Or are we watching another battery promise that still has years of reality to survive? We'll find out when these batteries leave the laboratory and start living on the road. And that is the part of this story I'm watching most closely. Subscribe to Modern Discovery, because this battery race isn't ending here. It's just getting started.